This is PulseClip, an IoT-based heart rate monitoring prototype connected to a web dashboard. The main components used in this project are an ESP32, a rechargeable battery, a charging module, a step-up DC to DC converter, a MAX30102 sensor, and an on and off switch.
This diagram shows how the components are connected. Power from the battery passes through the charging module, switch, and step-up converter before supplying the ESP32. The ESP32 is then connected to the MAX30102 sensor through the I2C communication interface.
The device program was developed using the Arduino IDE. This program initializes the MAX30102 sensor, processes the pulse signal into beats per minute, connects the ESP32 to Wi-Fi, and transmits valid BPM data to the web system. To use the device, the user places a finger on the MAX30102 sensor and waits for the reading to stabilize. The sensor detects changes in blood volume at the fingertip, while the ESP32 processes the signal into a heart rate value. The BPM data is then transmitted through Wi-Fi to the server. The backend receives and stores the data in the database, while the front end displays it through the PulseClip website. The website was developed in the anti-gravity coding environment. Its source code manages the user interface, data processing, database connection, real-time monitoring, patient history, and other website features. On the main dashboard, users can view the current heart rate value in real time. The website also classifies the reading as low, normal, or high, and displays the data through a continuously updated graph. As long as the user's finger remains on the sensor and a valid pulse signal is detected, new BPM data continues to be transmitted to the website. When the sensor is removed from the finger, the ESP32 no longer receives a valid pulse signal. As a result, no new BPM data is sent to the website, the displayed value stops updating, and the graph remains at the last recorded point.
Next, we will explore the PulseClip website in more detail. The system provides separate accounts for doctors and patients. Patient IDs and passwords are created and provided by the IT team. For this demonstration, we will log in using a doctor account. After logging in, the doctor dashboard displays an overview of all registered patients and their latest monitoring data. From this page, the doctor can select a specific patient for further review. In this demonstration, we will select Zydon. The system then opens Zydon's patient dashboard, where the doctor can view his current BPM, heart rate status, and monitoring graph. Next, we open the history page. This page provides a more detailed view of the recorded BPM data. The doctor can select a specific start and end time to review measurements from a particular monitoring period. The website also provides a manual data entry feature. This allows heart rate measurements to be added when a patient checks their BPM using another device instead of PulseClip. The final section is the education page, which contains basic information about heart rate, BPM categories, and factors that may affect heart rate. After completing the monitoring process, the user can click the Logout button to securely exit the system. In conclusion, PulseClip integrates heart rate sensing, embedded programming, IoT communication, patient data management, and health education into one web-based monitoring prototype. Thank you for watching.